Oh, thanks for having me. It's nice to be at my first Raspberry Pi event, and it's a really nice event actually. So I think I'll come to more in the future. So my name is Kevin Chetty, and I'm here on behalf of a startup company which has been recently formed by my colleagues Liban, who is here, and Paul Brennan. And we've just launched a new radar hat for the Raspberry Pi, a 60 gigahertz millimeter wave radar hat, which we call the DreamHat. Um, just about our kind of other lives. So I'm a professor of wireless sensing at University College London, which is just up the road. And both Paul and I, Brian, both work with all at UCL as well, and we're all academics. So this is kind of a project that we've been working on. Uh, More information about the DreamHat can be found on the website dreamboards.co.uk. You can follow us on Twitter, and we have an email address as well. And we're also recently been licensed as a powered by Raspberry Pi device. Okay, so just to start, I know all you guys are brilliant software engineers. I didn't know how to pitch it in terms of how much background you know about radar. So I thought I'd just do a bit of background first and then kind of dive into the DreamHat. So just a couple of questions. The first, does anyone know what radar stands for? Yep. Excellent. Okay, so yeah, don't have to explain that in any great detail, but yeah, we're using radio waves to detect and range, and it's been around. It's a technology which has been around for a very, very long time. Um, so with radar systems, a lot of the time they're thought of these massive installations with very wide area sensing, and usually think about military and air traffic control. So here's an image of some radar systems which are really huge. Here's the Heathrow one, on the bottom one on the red. You know, air traffic control. But like I said, these large installations, very wide area sensing. So here's an image on the right of the Pentagon, and it's generated using a technique called SAR, synthetic aperture radar. But again, just to highlight my point. And then another kind of use of radar, again, with these large installations and wide area sensing, is weather measurement. So you have these massive cells, measurement cells of kilometers. You have radars that go in the nose cone of an aircraft, etc. So these huge installations. But more recently, we're seeing radar coming into the urban landscapes. So, you know, for autonomous vehicles, it's not streaming that well, the images, but hopefully I'll get better because I've got a few images and videos for the presentation. But yeah, so, you know, for autonomous self-driving cars and self-parking, they're all kind of built radars in. Don't know if anyone has come across the Google Solly, which was a gesture recognition watch, where you would use gestures in front of the watch, so that would be turn the volume up and little things like that. And it was radar behind that, generating kind of signals which you can process and understand those gestures. So just very basic principle. I know many of you might understand what's going on, but the way radar works is that a radio wave is transmitted through an antenna towards an area of interest. It arrives at an object, so you can see the object there, and that object scatters that radio wave in all directions, and a very small proportion of it comes back into the original direction. We know the time it takes, we can measure the time it takes to travel there and the time it takes to return by just the total lapse of time between sending that signal and receiving the signal. And I promise this is the only equation I show for the whole presentation, but we can use our standard speed, distance, time triangle or whatever, and we can work out the range of that object. But radars can just do more than just detect and range. And I might kind of dive into that in a little bit. But yeah, so they're a nice kind of tool, and they've been around for a while. Another quick question. Has anyone ever heard of the Doppler effect? And okay, do you want to give it a go, someone? Just for the audience. Yeah. Excellent. Yeah, and I don't mean to. This is
for a demo.
yeah. This is a question I usually ask my students. So yeah, I know. I'm sure. Yeah, I'm sure you guys are all. I just thought I'd put it out there. I always ask my students just to get the you know, the right amount of kind of pitch it right. But as you said, a phenomenon which a wave experience, it changes its frequency, and it occurs when the wave source and receiver move relative to each other. And I actually do have a demo. So I don't know if the sound works, but this is just that's just from my laptop. So here's a car coming, and I'm ahead of you in my video, but you can hear that change in pitch as the sound goes by. So that's just a demonstration of the Doppler effect. Let me just mute this. So in radar, we use the Doppler. Oh, you can't see this video. You might want to see my screen, or maybe you'll see it. So actually, I've done some work in the past where we used Wi-Fi, and we would be able to measure people just in everyday environments using Wi-Fi. But the principle is the same here. If someone's moving around in a field, a radio field, you can see the change in frequency of those waves, and you can set the waves and detect the Doppler shift. So millimeter wave radar. One of the reasons that it's gained a lot of traction in the last few years, one is because it's very high precision. So when we say millimeter wave radar, we talk about high frequency radar where the wavelengths or the order of millimeters. And just maybe put it in perspective, Wi-Fi at 2.5 gigahertz is just kind of under millimeter wave radar. So it's kind of a lot higher frequencies than those. But it has the ability to track individuals and multiple people. It's even been shown, and actually some of my research group have shown that you can detect respiration, very small movements. So even as the chest wall moves back and forward, you can detect breathing. So things like signs of life, for healthcare and things like that. And also there's a technique which we've worked quite a lot on called micro-Doppler. And the idea here is that, so when there's Doppler, there's movement kind of going back and forth. And a lot of our Doppler measurements, we used to see a lot of noise in them, which were problematic. But actually, what they were was what we call micro-Doppler, and it was due to the micro motions on the body, so like swinging limbs, the torso moving backwards and forward, and all these very small motions called micro. And actually, so from being a problem, it allowed us to kind of delve in a little bit more, apply some machine learning and AI, and we could start to identify different types of movements based on these micro-Doppler movements. And so there's a whole kind of area of work there. Radar in general is contactless, so there's no requirement for wearable devices, which the elderly especially have kind of low levels of compliance, RFID tags and things like that. It also preserves privacy. So we sell radar a lot by the fact that it doesn't identify people, and so it has the element of sensing with privacy. Unlike video cameras, it can operate in low levels of light and also through smoke and fog. It can penetrate through materials such as clothing and even walls. So we've done some work where you can actually do through the wall sensing with radar systems. And what we're finding with millimeter wave radar is that it's becoming democratized. There's, the big areas like autonomous vehicles and those kind of areas are kind of mass producing the hardware. So it's really kind of bringing down the cost of these, of this kind of technology. So just a range of applications you can use this: autonomous vehicles, you can use it for smart home, healthcare, ambient assisted living, where there's a lot of elderly people kind of living on their own at home, and it's hard to kind of keep track of them. Human computer interactions, so things like gesture recognitions, robotics projects, and a range of kind of sensing applications. But the takeaway on kind of this slide is that as the hardware continues to shrink in size and cost, and we start to get compact single chip modules, these millimeter wave radars are now becoming a viable alternative and or complementary to traditional sensing, like optical sensing and acoustic sensors such as cameras, LiDAR, and microphones. But there still are some issues. Millimeter wave radar is a great technology, but it's primarily used in industry and academic research, just mainly because it's really complex and hard to get going with it. So in my own experience, when I have students working on radar systems, they're smart students, but just the learning curve to get up to grips with some of these systems. So this is a system by Texas Instruments, via an Israeli company, Infineon. So there's lots of kind of off-the-shelf systems out there, but there's a very steep learning curve with them. So it's hard to get going. But also, once the same students have spent years kind of learning about radar, and they want to get more into it, a lot of these systems are closed. So they want access to the raw data, and they just can't get it. And especially now with machine learning and AI, when you want that raw data, it's just hard to get hold of. So that was kind of our motivation for building the DreamHat. But one of the things we wanted to do with DreamHat was increase the accessibility of millimeter wave radar to a wider audience. And I've only got into Raspberry Pi the last few years, but a lot of my students are really kind of swear by the Raspberry Pi, and I've kind of adopted this and got on board with it because it's a really cool piece of technology and something that I've been pushing for a long time now. But anyway, the Raspberry Pi offers an ideal platform because it can introduce millimeter wave radar from the classroom to hobbyists without those high costs and complexity of traditional radar systems. So it has a very affordable and widely available, has a large user base, there's a global community and collaboration opportunities, especially those GPIOs. It makes it potentially plug and play, just kind of an ease to get a hat and put it on and put a hat on and kind of get going. The other thing is that you can integrate with other sensors. So multimodal and fusion is a big area at the moment. And the fact that it's portable and low power means you can deploy these in the field and kind of develop embedded applications. So we've kind of really focused on the Raspberry Pi to build this hat. So this is an example of the DreamHat. I've got one here if anyone wants to have a look afterwards. So we've built the DreamHat around the Infineon monolithic microwave integrated circuit, which is number 3 on that diagram there. And if anyone wants to see the board later, you can actually see the antennas kind of etched in onto the chip. So it's got one transmit antenna and 3 receive antennas. And for anyone who kind of knows about radar, that gives you directional sensing, so you can steer beams and you can look at direction, bring in directionality into your sensing. So we operate at 60 gigahertz, which is quite a kind of nice millimeter wave frequency. And we also use a technique called FMCW, which in the radio world is quite a well-known technique, frequency modulated continuous waves. The range resolution, so it's a really high precision radar, and it can give motion sensitive or detection sensitivity up to the order of 3 millimeters, so quite very sensitive. And this particular device can sense up to a range of 15 meters. It's low power consumption, so 0.5 watts typical. And when we built it, the Raspberry Pi Hat Plus specifications had just been released, so we kind of built it to those specifications. So if you look on the board, there's kind of gaps for ribbons, etc., for other devices and other apps or whatever else to kind of plug into the board as well. And it kind of just meets those specifications set out in that document. So when we built this, the idea was it to be one plug and play, so it can people can get going within 15 minutes. But also to make the raw data accessible. So if you want to do, once you had to play around with it and use our built-in examples, if you want to start doing anything cool with it, you have the raw data to do that. And also, another kind of future goal for us is to start building radar tutorials. I want to kind of speak to the Raspberry Pi Foundation at some point, and to maybe, for high school or whatever, we can start kind of introducing signal processing and RF engineering using this as a board and some tutorials around it. But anyway, so just like I said, as a first pass, for anyone who wants to play with it, there's some built-in examples. And before I show them, I just want to kind of just explain this graph here. So this is known as a Range-Doppler plot, and it's one of the classic visualization tools in radar. And what it does, it shows on the y-axis, it shows the Doppler or the speed. So this, you can't see my arrow. Okay. So the speed of the target on that axis and the range on the x-axis. So that's what it shows. And that line in the middle is called the zero Doppler line. So basically, everything that's stationary sits on the zero Doppler line. So all the kind of furniture, the clutter, everything which is why it's always kind of a deep, strong line. So that our first example is a Range-Doppler example. So here's, I'll see if this video works. So here's me. And what you can see is the DreamHat in front of you. I'm stationary. You can see my response as a stationary target. And let's see, what I do, I start rocking, and it's a bit more fluid on. And actually, if you want to look at our website or our Twitter channel, you can see it. But it's all in sync. It's probably a bit out of sync here. But you can see as I kind of rock back and forth. Yeah, like I said, maybe I'll show you this video later. But then I do one hand, and you can see my one hand and my body kind of in sync, asynchronous. And then I do one hand and two hands, and then you see the, and actually, like I said, on the video, it's a nice, you can see a nice circular movement. Not so great here, but that's fine. So that's the Range-Doppler with kind of gesture and hand movements. Then we've got another example. This is Liban, just walking back and forth. Let's see if it works. So what you can see, the great thing about this is that you can get direction on this. So as he walks forward, you can see his negative Doppler. As he walks back, his positive Doppler. And as he's further away, the signal gets weaker, but you see his distance and his range. No, the strength of the light, the brightness is his radar cross section. Yeah. Yeah. So the y-axis is speed, and the x-axis is range. I mean, I can play it again. So so you see as he walks forward, so he's at walking pace, so he's there, and then when he's walking back, he's in a different direction. So he's positive and negative Doppler. Yeah, and then you can see his range. Okay, let me move on. And so the example 2, we've generated a tracking on an X-Y map. And so what we've got here, and this is where the location of the DreamHat is at the top. The way we've built this is that whenever there's a detection, it shows up in bright yellow, but then over time, that detection fades away into the blues, the greens and blues. So it kind of leaves you with a track of the motion. So that's basically how it works. So let me see if I can get this working. So here's me walking in a circular motion, and it's just tracking me as I kind of walk around. Again, I think if you're interested in this video on the website and whatever, on our Twitter account, I've just posted these, that it's a lot more fluid, and you can kind of see the motion as I walk around. And then there's another example here is more of a random walk-in motion. So this is Liban just kind of walking back and forth, and yeah. And you see we've blurred out faces using our logo, which is a cool thing. Yeah, so yeah, so just kind of tracking as you walk around. Okay. So we're fully open source. Sorry. Next. Yeah. So fully open source. So on our website, you can see, we've just kind of made everything available. So you can see here the footprint, the physical specifications and the footprint, the schematics. So, like I said, anyone can kind of see how it's built and see how it's kind of made up of. Just upcoming in the future. So in the upcoming Raspberry Pi official magazine, which used to be called Magpie, we think they're doing a feature on us for the July edition. So something keep an eye out for us. And also we're hoping in July also to start selling on Pi Moroni. So you can buy these for our website at the moment, but obviously everyone knows Pi Moroni, and it's a nice shop window for us. So so hopefully as a startup we can actually sell some of these. That's pretty much it. So like I said, a quick kind of whistle stop tour through Radar and our DreamHat. And like I said, if you have any questions about it and interested, let us know. Thanks.
The best demonstration I've ever seen of the Doppler effect. Back in the 1970s, there was a sketch show run by a couple of idiots with the two rods.
Oh, I've heard of them, yeah.
So they did this sketch, and it's 18th century,
Right.
and they're policemen in a horse and carriage.
Right.
And they're sitting on carriage with hunting horns. And you can see the horses galloping towards you, and they're on the hunting horn. Ding dong! Down, picks two others up, and they went.
If it demonstrates the principle, then yeah, great.
How much are you selling them for?
they're going to be set as £100, so 99.99. Yeah.
You mentioned applications like observing someone is awake breathing. Is that resolution capable with a board like this, or actually not quite? And it's other.
Yeah, so there is so we've done some basic tests. So one thing we have done is just try to stand still in front of it, and because of the order of millimeter sensing, you can't stand that still. So there's always, yeah, but we haven't just because it's so new, we haven't done the experiments yet to look at breathing and heartbeat. But we just we've got an anechoic chamber, so we're actually going to go in there and just try and ping it and just see if we
Imagine to put it on a gun and
yeah. Well, yeah, I mean, there's a lot of radars out there already. It's just we've tried to make this low cost. So a lot of radars at the moment are the order of a couple of £1,000, and again they're very closed, so you can't get the data off them. But yeah.
So what's the interface? What's the opinion?
Yes, so Live, do you know much about the interface? Because I know Fangzan built. I know you can access the interface still with, because our examples are built of fixed parameters. So the way the FMCW transmits, and the step frequency, but there is scope to change some of those parameters through the Infineon interface.
Through the SPI, available on the chip.
Yeah.
Right, so it's an SPI connection to, and what you just write simple Python to say,
Yeah.
grab.
Yeah. There's some configuration code, isn't there, which we can just upload via SPI and yeah.
Asking the question a different way, all of the data is going across the port bus. What's going to connect them? Via that SPI.
Yes.
So how many pins are you using? Just the SPI pins, or there's other pins as well you need?
Yeah.
Plus power, obviously.
Liban designed the board. Yeah, so I'm more of a signal processing person. So yeah, anything on that he probably better fit to answer. We had, yeah, well, we've done a lot of that work in other work, but in another early prototype of this, we put a microcontroller unit, and one of my PhD students does a lot of edge computing and taking machine learning models and shaving them down and making them kind of deployable and resource constrained devices. So it's something we're working on, and we haven't done much on the DreamHat as of yet.
How do you compare with the tools? So you got an interlink that does pretty much all of it, and does like John as well. You got an ARA that's also millimeter wave that does zone, does grading, those all down sections, and there is CFD element on that compared probably 5 or 6 different millimeter wave, like about 10 pounds each.
Okay.
So how do you compare this market?
Yeah.
Something that's quite high in the price.
Yeah, we've seen some of those which we've seen are the 24 gigahertz. There's a 60 as well. Oh, right, okay. Yeah, I mean, I see. I think there is this range. So there are some of the ones I showed there. The kind of via ones, or whatever. They're the order of thousands, and then you've got some of the ones you mentioned, which are less than £100. So there's this huge range, and I suppose what we've seen with those ones are, again, when some of my students have been using them, they've just been hard to get up, and they're not plug and play in a sense. So
you want to use that in the zone, so you can just the data out of it.
okay.
Within the zone, gets the data out.
Yeah.
There is another own systems open source one that's again has multi-millimeter wave temperature sensor, PR sensor all together, and it's about 50 pounds.
Okay.
So it's kind of like a trade-off, like, well, what do you get more with this one rather than that one? You think that's, well, then you can get more data.
Yeah.
And it's kind of the same chip. Yeah,
Okay. What? Yeah, I suppose we'll have to look at those chips and just do a like for like comparison and kind of understand what we're getting with ours, with our chip. And I mean, with I don't know, is it if it's FMCW, but FMCW requires quite a lot of heavy processing, like deramping and
that's really sweet.
um I don't think we do we, live art? No, we don't. No, but with yeah, so with our with this radar, you have to send kind of these chirps, these frequency modulated continuous waves, which are very good for Doppler. Because they're very sensitive. So again, yeah, if those ones, and I'm not sure if those other millimeters are. Yeah, well, it's actually the radar architecture. The radar architecture is, you can get kind of pulse radar, which is good for certain things. Whereas with FMCW, it offers benefits. So you get there's a lot of kind of it can ease the processing, it can lower your ADC requirements and your dynamic range. So how sensitive you are to some of the weakest, very weak signals. So I think, if, for example, here, for example, with the breathing, for example, it's only very small movements, of the order of millimeters, but because of the sensitivity of the high dynamic range that we can kind of detect those very minute movements. But I'm not sure. So the chips you mentioned might be able to do that as well. I'm not sure. I have to look. Yeah, but I think it's definitely worth us doing a kind of a quantitative analysis of and see what we're offering. Yeah, I suppose because we're quite new, we're still kind of figuring out the landscape. Yeah, yeah. And I think, yeah, yeah, yeah. What you made up against? Yeah.
These, you have like two channels or something, where generates the sinusoidal.
Okay. Yeah.
The other one's not like the receiving frequency of this, and then the other one is for Python.
Okay. Yeah. And I'm wondering how many channels it, because our chip has one transmit and three receive, which gives you a lot of spatial diversity. Okay. Is it one transmit and well, yeah, I suppose.
Place them chips.
Yeah.
Like, 4 or 5, and they support different chip on.
Yeah.
I don't follow them
Okay. That's good.
with chip one
It's good.
on 5.
Yeah.
Like through the mission thing,
Yeah.
self-contained, and quite small, like a little point shape.
Okay. Okay. Cool.
Like your 2D representation, actually. Make sure you understand what is there, not that in this one frame.
Yeah. So again, I think the Cartesian map is where we can, which is what the processing and the radar and the FMCW allows us to kind of to do. So yeah, but I mean we're still developing as well. So yeah, we're still kind of trying to build out more applications and things like that. So for example, here with the Range-Doppler, you could have multiple people moving around and seeing responses for everyone. This example is really focused on one person, and it kind of falls down when you get multiple people here. So again, we need to look at kind of, there's a lot of algorithms, multiple hypothesis tricking filters and Kalman filters. Yeah, using, yeah, I guess, yeah, it's good. ESP home.
It's a many almost is big place, but common it's simple. They are made drivers and everything with that play with some configuration and do that.
So there's a couple of questions up in the chat.
Sorry, yeah.
So Bruce is asking, your 15 meter range restriction, is it practical to lower frequency and get greater range?
We've played around with that, haven't we, live on with the drone experiments. Yes, we're playing around with that at the moment, and it seems to be working quite well. So we're working with some some people from the British Antarctic Survey who want to mount it on a drone and work with kind of higher ranges. So we've kind of changed the code to just lower the frequency and some of the transmission parameters, and seems to be working, but we're still kind of testing that out.
So it can still use the same hat, you're just changing the parameters of the hat.
Yeah, just changes the parameters of the transmission signals.
Right.
Yeah.
And the other question Bruce has, it senses, has 3 antenna and you can steer the beam, could you detect a person in a particular direction?
Yes, that's kind of all built in, right? So all the beam steering is actually, a lot of it is array processing on receive. So as the signals come in, you can do array processing, and you get directionality that way. So yeah.
So you get separate signals from all 3 and
Yeah, so basically it's everything in, and when it processes, it puts a kind of a phaser on that, the post-processing, and it can look at sensitivity in different directions to get direct, and
Right.
which is why in this particular example, if I'm walking in a circle, it can find your direction.
And which Pi version are you using?
This works with we use the 5, but it works with Raspberry Pi 4 and 5.
Right, and you got enough processing, enough oomph there to keep up.
Yes, yeah, seems to work well with everything so far.
Very small.
Yeah, so it's all about the radar cross section. So maybe a small metallic object or a large, so but basically everything, it all depends. Yeah, everything has a radar cross section. As a kind of standard, a human is 1 meter squared or 0 dBm. So, or 1 meter squared. So and then anything metal has a higher radar cross section. Anything, certain other materials, it might be transparent, which is why we have radomes and that plastic material. So in answer to the question, it probably could detect something small, but probably with some metal in it, maybe. Yeah. Yeah. Well, actually, it's going too fast sometimes. So it's your radar parameters. So it can detect very small movements. But when you go too fast, it might fall outside of what you can process. But again, you can change the radar parameters to have more sensitivity to higher velocities. Yes. Yeah, Doppler resolution. Yeah, so you can kind of, yeah. Yes, potentially. I mean, there's a number of ways you could do it. You could put it on a door, the easy way, and just count people at sensor. Or you could have it somewhere with I can't remember the beam width. It's got a quite wide beam width, the antennas, and not the XY map, but the Range-Doppler map, or just the raw data. You can look for Doppler as a function of direction. So, because what you can look for is actually small changes in frequency, and then kind of find the direction of those. Yeah, I mean, you can put it on a door and just have sense. I mean, I suppose there might be occasional trip ups if 2 people walk at the same time, but if you build in a huge RCS, if you build in like a massive RC, a massive reflection, maybe you can infer that's 2 or 3. But I suppose you'll need a library or some kind of intelligence behind it to figure that out. Yeah. One of the other things, I mean, we've done is we just did an experiment. We just had lots of people walking around the room, and rather than going the radar route, we went the machine learning route, and we just trained on, this is what it looks like. It's all messy, but this is messy A when there's 2 people, messy B when there's 4 people, and messy C when there's 6 people, and it learned those characteristics and it just spat it out to us. So yeah, that's a lot from you, Dan. Cool, thanks.
Is there any other questions from anyone online? Yeah, so Anthony's asking, wouldn't you expect longer wavelengths to penetrate walls better?
Yes,
Why
100%.
is millimeter radar good for that?
Yeah, I mean, typically through the wall radars are low frequency because of is the penetration resolution trade-off. And through the wall radars used by the military and the police, etc., are lower frequency. But millimeter wave does have some penetrative capability, but you get that resolution. A lot of millimeter wave radar is focused on resolution, but it has some capability which you can potentially exploit. So,
Right.
for example, even like plasterboard walls, we find it works quite well for plasterboard walls, not so much brick. Whereas our other radars at lower frequency work really well, through bricks and things like that.
Bruce asks, what data do you get back to the Raspberry Pi? Is it an array of values? Can you process on the Raspberry Pi to produce?
It's a complex. It's complex values. Yeah. It's a raw complex IMQ data, which
Okay.
is standard radar outputs. Yeah, that's correct, isn't it? Yeah.
Any other
Yeah.
questions from anyone in the room? All good.
Oh, thanks.
Thanks very much. That was really cool.
Very much. Good.